This is the walkthrough video for PCTC 2022, round 2, question 12, spellbook. So as the last question, this is obviously going to be extremely difficult, and the question itself takes a while to understand. But essentially the question says, or the question gives us a list of pages, and on each of these pages there's a number that points to another page, and it asks us what's the longest chain we can make by using this page pointing to another page system without visiting any page more than once. So we'll get started with this, but before we dive into the algorithm, let's just do the easy bit, which is taking our input. So the first number is how many of an input we're given, and then the next that many numbers is our real input, or the pages. So let's create a list called pages, and let's have a loop that runs as many times as our first input number, and then for that many times we can take in a new input as an integer, and we can append that to our pages list. Okay, so now we processed our input. We've got in this case, we've got our 6 numbers, and they're all in a list format. So now it gets to the algorithm bit. How on earth do we solve this problem? And there are loads of different ways of solving this problem. I think it's a really cool question because you will probably start off with a really inefficient method and maybe get 4 or 5 marks out of 10, and then you'll work your way through and try and figure out how can I make this more efficient. Keep on asking that question, and eventually you'll reach an efficiency that gets you 10 marks or 10 points. And this is also quite cool because you have to make sure it's both efficient in terms of a time perspective, so once in 3 seconds, and that it's efficient in terms of a memory perspective, so that you don't use a gigabyte of RAM, for example, to run your code. And so that there are 2 metrics that you have to balance when it comes to efficiency in this case, and that's even cooler as well. So what I'll do is I'll talk about my method for solving it and the brute force method for solving it. I'm sure there are loads of other methods out there, perhaps even more efficient methods than the one I come across, but this is one that hopefully should score us 10 out of 10. So let's get started. So I've got our 6 page input numbers in the example, and I've written them out here. And I always like to visualize things. Like when I'm in a competition, I would always have a pen and paper and just draw things out constantly. And so in this example, let's draw out our 2 answers. That's 2, 5, 1, and 3. That's page 2 to page 5 to page 1 to page 3. And our second answer would be page 4 to page 3 to page 5 to page 1. So page 4 to page 4 to page 3 to page 5 to page 1. Is that correct? 4, 3, 5, 1. Yep. So these are the 2 longest chains that exist in our example input. But yeah, I guess before we talk about the efficient solution, what's the obvious solution? The obvious solution is going to be the brute force solution, where we go through all of our pages in order from left to right. So in this case, we have 6 pages, and we look at each of those pages, and we calculate the longest chain you can make if you start at that page. So if I start at page 1, what's the longest chain I can make? I write in basic code. This is relatively easy. I write in basic code to figure out the longest chain I can make. That's going to be like 3 to 5. So page 1 to page 3 to page 5. And I can't go back to page 1 because I've already visited page 1. That's what I started off at. And so the longest chain there would be 3. And I do that for each of the pages in my book. And that seems pretty easy. That seems like it should work, and it would work. But if we look at our constraints, and of course this is question 12, so it's not that easy. So if we look at our constraints, it says the amount of pages you can have varies from just 2, which is good, but it goes up to 300,000. And again, that may not sound like a huge number because computers can do things really quickly. But imagine if, 300,000 represents the length of the possible longest chain. So imagine if our longest chain is only, say, 100,000, but let's say there are 1,000 different pages that have a chain of 100,000, and then you just get really, really huge numbers. And so this program would take a huge amount of time to run because you have huge numbers combined with huger numbers, and that just leads to even bigger numbers. And that's going to take way more than 3 seconds and way more than 64 megabytes of memory to run. So let's not do that. And then, of course, the next question is, how can I make that more efficient, right? Like this brute force algorithm obviously works, and it will get me a few points. But how can I turn that into a much, much, much more efficient algorithm? And you can think about this for a couple of minutes if you want to pause the video. But I guess perhaps the first thing you may think of is the key issue with the brute force algorithm is I'm going through every single page and calculating every single chain length. And your aim to make this more efficient is to not have to calculate every single chain length for every single page. If, for example, out of our 300,000 pages, if I can get away with calculating just 500 of those pages, then yes, of course, our algorithm is going to run really quickly. And so if we find a way to chop down the amount of pages we need to calculate, then we should be able to get a good answer. But the next question is, how on earth do we actually do that? And well, this is kind of like a similar idea to dynamic programming if you come across that, which is when you calculate something, you might as well store what you've calculated, right? You should store what you calculate because it might come in handy later on. So if I've calculated a certain chain, maybe knowing that chain can come in handy later. And maybe if I already calculated that, I can use that information. So this is almost like a dynamic programming question, right? Because as you calculate an answer, you can save those answers, which means as your program runs, you can use your pre-calculated answers to calculate new answers. And that makes everything much more efficient. And I guess that's where the memory constraint comes in handy, well, comes in to bite us, because it means we can't store absolutely everything. If we store absolutely everything we calculate as we calculate it, we're going to run out of memory. So you need to be smart and only store the most useful things that we need and nothing else. And that way we should be able to cut it down. Okay, so now let's get into the actual algorithm itself. And so the way I noticed this is basically I looked at this example input and I noticed that the two answers are 2513 and 4351. And what's special about these? What do these both have, right? They both have this 513, this 351. Like, there's got to be something there, right? So let's go back to our diagram and let's draw in, for example, chain 5 to 1 to 3. So that's going to be page 5 to page 1. Let's make that a bit more obvious. Page 5 to page 1 and page 1 to page 3. And this is interesting. So if I do that, then where do I go from page 3? From page 3, I go back to page 5. So this is a loop, right? We've created a loop from like between these 3 pages. If you were to start at page 1, you can go through this loop and end at page. Sorry, if you were to start at page 5, you can go through this loop and end at page 5. Same for page 1, and same for page 3. And that means any page in this loop has the same possible maximum chain length, right? The biggest chain you can get from page 1 is these 3 numbers. The biggest chain you can get from page 3 is these 3 numbers. The biggest chain you can get from page 5 is these 3 numbers. They're all part of the same loop. And once you're in that loop, you don't escape from that loop, right? It's kind of what this entire problem is about. This entire problem is about loops. And as soon as you're in a loop, you don't escape from it. And maybe we can use that, right? Because if we've spotted a loop, for example, we spotted the page 1, the page 5, the page 3 loop, that loop, then we've already found, by computing the longest chain length from page 1, we've already found the longest chain length for page 3 and page 5 at the same time, because they're all in one loop. And now you may see where I'm going with this. So as we calculate the maximum chain lengths, if we find a loop, we store the loop. Because if we store the loop, we can figure out which other pages are in the same loop. And once we figure out which other pages are in the same loop, we've already calculated that. We don't need to calculate them. And this instantly cuts down our 300,000 page sample to maybe like a few thousand. I don't actually know, but it probably does cut it down. It cuts down by orders of magnitude, right? Because for every loop, let's say you have a loop that's 1,000 long, you've just cut out 1,000 pages that you now suddenly don't need to even calculate at all because you've already done that. And so this is the key insight, like one of the few key insights you need for this problem. So before we get into more of the algorithm, let's code this up so far. So let's start off with the same idea as like brute force. So we're going to go through every page. So for I, R in enumerate pages. If you haven't come across enumerate, it basically just says it's like a normal for loop through a list where R is going to be the element in the list and I is going to be the index in the list. And so this way we get the page number and the value on that page. But of course, as we discussed right at the beginning, because this is Python, it might be quite difficult because Python zero indexes things. So the first element in our page list is page 1. So like the 0th index in our page list is page 1. The 1th index is page 2. And that's just annoyingly complicated. So let's just add a 0 there. And now our indices should match the actual page number, because humans start counting from 1, Python starts counting from 0. Let's fix that by already adding just a random number to our pages list. So what this actually does now is I represents our page, the page number, and R represents, I guess, whatever the next page number is going to be. So what should we call it? Let's call that next. Yeah, that should be fine. I'm not sure if we actually need the value of R in our solution, but let's keep it anyway. Oh, sorry, the value of next in our solution. Let's keep it anyway. We can always remove it later. So we want to, for the brute force solution, we want to go through, we want to find the longest chain for each of our pages. So for a given page, the longest chain ends when we've visited a page twice. And so let's create a while loop, right? Because while, wait, let me just check something. Okay, so yeah, I don't think we will need next. There's no point having next. Let's scrap that. A page in range, and let's do for page in range, len pages. Okay, and the reason we're going to scrap next is because we're going to use the word next as a useful variable name. So let's say while the next page is not in the visited, so okay. So this line of code, we need to create the variables, but this is basically saying if as long as our next page that we're pointing to is not something that we've already visited in this chain, then let's go ahead and continue. But we need to keep track of all of this. So visited starts off as empty, and next is going to be initially it's going to be pages page. Pages page, and yeah. Now we can finish our while loop to finish our brute force solution. So every time we visit a new page, let's add it to our visited. Yeah. Let's first add a new page to our visited. So let's do visited.add whatever page we're currently on. So let's do the next. Actually, let's do, yeah. Okay. So next is a slightly misleading variable name. Because next represents the next page relative to everything we've done so far. But because before we've run the for loop, we haven't done anything, we're kind of like blank, right? So next represents our starting point when our for loop is first run. So we're going to add next to the things we visited, and then we're going to update next to be equal to the actual next, which is this from earlier, because this will just point to the next page according to our input. Again, this is all really confusing because we have numbers pointing to other numbers. But yeah, once we have that, that's pretty much it, right? Because the length of our visited set is going to be equal to the length of the longest chain that you can get when starting at that page number. And so this is basically our brute force solution, right? We just need to add a few more lines of code if we were to actually code a brute force solution. We're not going to bother with that because we know that's not going to work. Or at least it's not going to work in 3 seconds. So what we now want to do, so we want to say after we've found the longest chain of a given page, we want to now keep track of the loop that we found. And now this is where we might come across the first issue, because, for example, the loop in these two answers is 351, 153, whatever you want to say. So let's say it's 513. But for example, this chain, the entire chain is not loop. The entire chain is not loop. Only 513 is a loop, and that should be relatively obvious if you were to look at the answer, right? The loop never visits page 2, and so the loop is only pages 5, 1, and 3. And so this is the loop. And so we need to basically figure out where is the loop in our chain. How do we figure out where the loop is in our chain? Well, we know this is the loop because once you've gone through every number in the loop, then you go back to the start of the loop, right? So if we were to continue this chain forever, we'd get page 2 to page 5 to page 1 to page 3, back to page 5, back to page 1, and so on. So we know this is a loop because we have this repeating pattern, 513, 513, 513, 513, and so on. And so that's how we know what loop it is, where the loop is. But of course, to do that, we need to keep track of the order of the pages we visited. And a set doesn't do that. A set just keep track of everything in a jumble, but we want the order. So let's do visited list, and let's make that list. And whilst we also add something to our set, let's also add it to our list as well. So visited list.append next. Now, the reason we have both a set and a list is a set is really fast for checking if something's in it or not. So that means this statement would run basically instantaneously or instantly. And that's not true if this was if we had visited list here instead, because just because of the mechanics of Python, checking whether something's in a set is a billion times faster than checking whether it's in a list. And so where possible, you want to use a set. And this is going to come into play for our under 3 seconds requirement. And so once it does increase the memory, we're going to hope that it doesn't increase it too much. And we'll figure that out. So yeah, that's the reason we have both a set and a list, is so that we can have the best of both worlds. We can have the quick checking there, and we can also have the order. And the order is important, as we discussed, to figure out what the loop is. So now let's figure out what the loop is. And the loop is going to be, from visited list, it's going to be the index of next, right? And why is that? Is because this loop finishes if the next thing we want to visit, we've already visited in the past. And so we need to figure out where we visited in the past. And this is how we figure out where we visited in the past, by looking at our visited list. And so let's say our first encounter, for example. So our first is where we first visited it. And why is this useful? It isn't really useful. It's a stepping stone to get what we want. What we actually want is, how long is this loop? How big is this loop? Is it 3 pages big? Is it 5 pages big? Is it 100,000 pages big? And the way we do that is, let's assign this to a variable length. The way we do that is by finding how long our entire chain is. That's going to be len visited, how long our entire chain is, minus first. Yeah, this should be correct. So if you visualize it, I guess, let's visualize it here. So our chain was, what was it? It was 2513. And then in theory, the next number is going to be 513, 513, and so on. Let me just scroll down. There you go. So when we reach this variable, this is our next, right? And this is where the loop breaks, because next already exists in our visited set, in our visited list. And so this is where the loop breaks. And so to figure out the length of the chain, we look at where we first visited it. And this was a index, what index is that? That's index 1. And how long is this overall list? This list is length 4. And so the length of the chain, of the loop, sorry, is the length of the chain minus the first occurrence of the repeated number. So that's going to be 4 minus 1, which is equal to 3. And of course, that checks out, because our loop is indeed 3 numbers long. So it's good just to check your math with a really small example to make sure it's correct. So now we figure out the length of each loop, of the loop. Now we can go through each of the numbers in the loop, like pages 5, page 1, page 3, and we can say that we already know the answer for that page, right? We already know the answer for that page. Let's just save that data, like in a dynamic programming question. You want to save something as soon as you calculate it. So let's save that. And to save that, let's create a new dictionary. Let's call it answers, because it contains the answer of the longest chain for each page. And we want to essentially add answer page number, which we'll define a bit later. Answer page number should be equal to length. But of course, now you might see another issue with this, right? If you start at 5, our maximum length is 3. If you start at 1, our maximum length is 3. If you start at 3, our maximum length is 3. But if you start at 2, our maximum length is 4. So we need to go through only the page numbers in our loop, not the page numbers in the whole chain that we just calculated. And so let's make sure we only go through those page numbers. So we're going to say for, I guess, let's call it I, for I in a range, and it's going to be the first occurrence to the len of the entire thing. Right, so what this for loop does is it essentially goes from 5 to the end of the list. So it ignores everything before the loop, it only looks at the loop. And so we're only going through the indices of the loop. And for each of those indices, let's make ans not I, because I is the index. And what's the actual value going to be? The value is going to be our visited list I. So I is the index of the page number in our visited list. And we're going to have in our answer dictionary, we're going to have that equal to the length, which is the length of the loop. This is all a bit confusing. There's so many random variables, so many confusing things that interplay with each other. So feel free to code along as you go and pause the video to experiment with how, if you slightly change the maths, like say if I added a +1, why is that not correct? If I added a -1, why is that not correct? Or print things out as you go along. Always print things out. The beauty of Python and coding is that you can always mess up. You can always experiment with it and just delete it as soon as you're done. You can always delete that line of code if it's broken or change it and no one will ever know. And that's how you best learn and build up an intuitive understanding of what this code is doing. Okay, so what we've done is we've found our loop and we've basically got the answer for every item in that loop. And now we've dealt with that, let's deal with everything that happens before the loop. So for example, in this case, we're just dealing with page 2. And so that we're going to basically copy this code, but we're going to have obviously a different range because we've already, that's just how it works. So for I in range, we're going from 0 to first, right? Because everything up until the first page in our loop is going to have a different answer. So we've already covered everything in the loop. Now we're covering everything up until the first page of the loop. It's going to be a very similar thing. Ans visited list I is going to be equal to length plus something, because the length the length is the length of the loop. So for every step we take left to the starting position of the loop, we need to add 1, right? Because as we said before, the length of this chain is the loop plus 1 is 4. It's not the loop itself. And how do we do that? Let's say that's going to be equal to length plus first minus I. So this is a bit confusing, but it basically says our answer is going to be the length of the loop plus however far to the left our current number is. So in this case, it's going to be 3 plus that 1. And let's make this a bit clearer. So this is obviously not the actual input case at this point. But let's say we had a load of random numbers there. I don't know, like that, for example. Let's say that was our longest chain. Then what our code is going to do is it's going to take the 3 and it's going to do the +1 here, it's going to do a +2 there, and a +3 here. So it's going to be 3 plus each of these, like that. And that's just calculated by that's one jump, that's a second jump, that's a third jump, and that's how you calculate these pluses. Okay, so we've got that sorted, and that's like pretty much the algorithm done, right? But then you may spot another issue, which is that our solution is still ultimately brute force, right? Like we're still going through every single page. How do we stop that? Well, let's say if we've already calculated our page, then there's no point calculating it again. And so let's just keep track of calculated. And let's make that an empty set to begin with. And let's say if page in calculated, so if we've already calculated it, then let's just continue this for loop. Let's just go back to the start of this for loop and continue with the next page number. And we also need to make sure that to calculated, we add the pages that we've already completed. That's in this case visited list I. Oops. And it's going to be the same thing down here. Okay, so just to recap, what we've done is we've now kept track using a set of everything we've calculated so far. And again, we're using a set just because sets are quicker than dictionary. I think in this case that may not be correct, but generally speaking, sets are the quickest method to check if something's in something else, like we did there and like we did there. So that's why we're using a set. Okay, so now it seems like our algorithm's pretty much done, right? So let's essentially just write out the final few lines of code to calculate the things we're interested in. And one of the things we're interested in, what's the maximum length of a chain. So that's going to be, let's say final answer is going to be equal to final answer 1, because we need to print out two numbers. First number we're going to print out, final answer 1, is going to be the maximum of, what did we call that? Answer. The maximum of the answers, of the keys in the answers. No, the values in the answers, because the value represents the maximum chain length at that point. And final answer 2 is going to be it's going to be all of the answer values and how many of them are the maximum chain length. And because of the way Python works, we need to turn this into a list, I believe. Yeah, this is actually not a list. This is like an object. And you can't use the count command on an object, so we can convert that to a list. Okay, now if we print off final answer 1 and final answer 2, we should get a score. And I say that because we may not get the full score, because there's still more optimizing we could do. Of course, as you code this, you should do the problem, you should write the code, and you should run it. Even your brute force solution, just run it, right? See how many points you get. See if you need to optimize it further, because you can reach a point where you don't need to optimize it further because you've already got 10 out of 10. There's no point in spending another 20 minutes optimizing it even more if you've already got the full marks. So what score did we get? We got runtime error, but I feel like I saw a 7 there. I think, yeah, recap the video and you might see a 7 there. So it seems like our code kind of works. Let's just make sure it works on this input. Oh, visited list not defined. I just made a typo. Visited list, visited list. Oh, yeah, there. Was that where it was? Line 32. Yeah, okay. 2 and 3, that is not the correct answer. Max answer.values. More live debugging, this is always great to see. So paging calculated, we don't want to do that. Ans visited I equals length. That looks good to me. Length plus first minus I, that looks good as well. First equals visited index length, s is len of the whole thing, minus first. Where have we gone wrong? Visited.add next, visited list.append next, next equal pages, page, oh right, yes, this is an obvious issue. Next is the answer to that. Yeah, sorry about that. This is, yeah, sorry if you got confused 20 minutes ago when I wrote this line of code. Yeah, I meant to write next there. And now, yeah, now we do see the correct answer 4 and 2. And so let's just submit the code and see how many marks we do get. Probably not 7. So we seem to be getting some, yeah, we seem to be getting some. How many would we get? Ooh, that's 5 or 6 so far. Oh yeah, so now it seems like we're having issues with our answer. Yeah, so we only had 2 issues so far. Yeah, so we got 8 to 10, which is still like really solid. If you got 8 to 10 in the real thing, and you had other questions to work on, go ahead and do that. But we want perfection, right? We want 10 out of 10 here. So let's figure out how to do that. And what's the issue? It says time limit exceeded. So our algorithm is correct, and that's always good to hear, right? Because it's not a wrong answer. It just means we've spent too long on our algorithm. So is there anywhere else where we can optimize this code? And yes, there is. And this comes back into our 2 examples, in fact, because say we've already calculated this chain. We've already found chain 2513. And we've already found loop 513. Well, when we calculate this, what's the point once we go from 4 to 3? What's the point of even bothering to look at the 5 and the 1, right? We've already calculated the answer to that, right? As soon as we reach page 3, we know that the rest of the chain is going to be 3 in total, because that's how long our loop is. So you can imagine, for example, let's say, can I think of a way to draw this out? I'll try. Let's say we had a loop of 3, 5, 8, page 100, page 50, and so on. So let's say we had this really massive loop, and let's say the last element, last digit in the loop is 6. So you have this massive loop, and this is, let's just put that in brackets. This is our loop, and we can have any number of pages before our loop, right? For example, we can have, say, 2 before our loop. Maybe we can have a 9 before that. Maybe we can have a 1 before that. Maybe we can have a 15 before that. And so the point is, we've calculated our loop already. We've got a loop, but we can kind of have an almost infinite amount of numbers before the loop. And so this means that not only do we have to calculate all of these numbers, we have to calculate the entire loop again, right? Because let's make this even clearer. Let's say this is our loop. There are so many different ways of getting to our loop. For example, like potentially, I'm going to assume there are because that's the only explanation I could come up with. That's obviously not right. Let's say 51. So let's say this is our loop, right? And there are 3 different ways to get to the loop. For example, let's say there's this way, there's this way, and there's this way. And that means that once we've calculated this, great, we found a loop. And then once we calculate this one, well, we found a loop. We found the same loop again. What's the point of going through this entire massive loop? What's the point of going through that entire loop if you've already calculated it, right? And we do that again down here, right? We start on page 51, then we visit our loop and calculate the entire thing again. That is just a massive waste of time. We should not be doing that. We've already calculated this. We should use that information, and we've already in fact stored that information in a dictionary. Why aren't we using that? And that is the reason why our code is still too slow for a couple of the big test cases. Because when our loop is really big, we just keep calculating the same loop again and again. We keep finding the same loop. We keep running this code for the exact same loop. And we might as well, like, once we've reached 3, we might as well stop it. Once we reach 3, we might as well stop it because we already know the answer at that point, right? We've already calculated the loop. And so let's implement that in the code. And hopefully that's going to be enough to get us those 2 extra points. So where does that calculate? That goes in here in this while loop, right? Because the while loop is finding the chain, and whilst we find the chain, as soon as we found a number we've already calculated before, we don't need to do that. In fact, yes, there are actually multiple cases to this, even better. Let me copy that. So what I described is one potential issue. Now we can have the same issue appearing in a different form. For example, let's say we have that. Let's say we calculate this. That's great. We've never seen any of these numbers before. Then let's say we calculate this. Well, we've already seen a 2 before, so why are we seeing anything beyond the 2? And same for this thing. What if we then calculate this? Well, we've already seen the 9 before, so why are we calculating any of this? Same thing again. We've already seen the 1 before, so why are we calculating this? We've already calculated all of this. Why are we calculating all of this again and again and again and again? And so essentially, what we want to do is, as soon as we found a number we've already got the answer to, we want to stop there, right? Because as soon as we come across a 1, which we've already come across before, we've already got the answer to that chain. And there's no point doing anything else. And you'll see what I mean when I code this up. So let's say if next is something we've seen before. So if next in calculated, so if it's something we've seen before and found the answer to, then what do we want to do? We want to say length is going to be equal to answer of next, because we've already calculated it. And so what I'm doing is I'm basically saying, say I had, let's delete that to make it a bit more obvious. Let me just draw something else as well for later on. Okay, so let's say we've got this far so far, and now let's say we're calculating this. We've calculated the 15. We found the 15. We found the 1, and now we found the 9. We've already seen the 9 before. We've seen the 9 up here. Let's delete that. We've seen the 9 up here. And so as soon as we've seen the 9, we know the answer to the chain starting at page 15 is going to be the answer to the chain starting at page 9 plus 2, right? It's all of these numbers plus these 2. So it's everything from page 9 onwards plus the 2 we've already come across just now. And so the answer to that, so length essentially here, the variable length I'm saying is equal to the length of this chain. We've already calculated it. There's no point going through the whole while loop again to calculate the same thing. So we've already calculated that, and that's what length is equal to. And so now the next step is, and you might see a parallel to this idea up here, because it's a very similar idea. The logic is the same, just applied in a slightly different part of the code, or the part of the algorithm. And we want to go through every number before the one we visited so far. We want to go through every one of those, and we want to essentially do what we did down here, right? We've got the length, and we want to add however many numbers appeared before the length to that. And so we can basically just copy the code. So for I in range from 1 to, let's go from 1 to len visited plus 1. And the reason I'm doing it this way is because it's a different way of writing this for loop, and you'll see why it's a bit more useful. So just like if you saw my question 11 video for this year, I think it's question 11. Yeah, if you saw my question 11 video for this year, what we're going to do is we're going to, one second, let me just write that. No, we're going to say our answer of visited list, and this is the key bit. This is where I say minus I. So what we're doing is we're going from right to left. We're going from 1 to 15 and so on, and leftwards. Actually, this is more confusing. Let's not do that. Okay, scrap that. Let's just do what we did down here. So if I in range up until, for I in range len of everything we've visited so far, what we're going to do, we want to basically just copy these lines of code. So that's ans visited list I. That's going to be equal to length plus first minus I. We don't have a first, so first is basically going to be the length of the entire list, I believe. I think it's going to be that. We'll verify that later. So yeah, so we basically want to add the, like, at this point our list is, for example, 2 digits long, two numbers, 2 pages long, for example, and we want to add as many pages that you need from here to get to here. So if we're on index 1 and our length is 2, then 2 minus 1 is 1, and it's basically just the same idea as here. It's just that we're not dealing with loops anymore. We're dealing with pre-calculated answers, but it's the same idea up here. And again, it's difficult to explain, but it makes sense once you think about it. And if not, just pause the video and have a play around with this as usual. And that should be the answer to that. And now we want to add it to our calculated as well. So let's just basically copy paste that. And now I believe this should give us full marks. No, that wouldn't give us full marks, because once we've done this, we then want to break out of it. Like we've got the answer already. Let's break out of the while loop. But if we break out of the while loop, we then run all of this code, which we don't want to run. Like we've already done the calculations up here. We don't, like, this won't work. We don't need to do this. This code that I've highlighted here is only to deal with loops, whereas this code is to deal with pre-calculated answers, which is 2 slightly different things. That's why our code is very slightly different. So yeah, we don't want both codes to run, both snippets of code to run on the same page number. So let's add this nifty little Python trick, which is else. Let's make sure that's the correct indent. And else basically runs if you haven't broken. So if you break out of this while loop, none of this is run. If you don't break out of the while loop, this is run. And so that means if we break out of the while loop here, which means we've already run this code won't be run. So this is just a cool way of basically selecting which code snippet we want to run when, and to make sure we only run one of them as opposed to both of these snippets of code. And now this should give us the full answer. Please say 10. Or we have some more live debugging to do if it doesn't say 10. 10, yeah, perfect. So yeah, this is a really long question with really difficult algorithmically. But well, my technique is always just to draw things, to visualize things, to think about things like this. But remember, always you might as well just write out the brute force solution and then iterate it over time. That's what we did, right? We wrote down this one and this while loop, and then we slowly developed it over time. We went from getting, what did we initially get? We got when we fixed the code, we got not 8. That doesn't make sense. Yeah, we probably didn't get 8. We just got a really low number. We would have got a really low number, and then we iterated it and fixed it a bit more, made it a bit more efficient, and got 8. Then we made it even a bit more efficient even then, and got 10. And this code actually, when I was coding this, I did a couple of things that were just as quick, but slightly less memory efficient. So my code is quick enough, but it broke the memory constraints that we have in this question. So always just be careful. Once you've got the correct algorithm, try and figure out how you can slim it down a bit more. How can you eliminate all of this extra memory that you're writing? And so in this algorithm, we do use quite a lot of memory, but we use less than the 64 megabytes that we're given, which is good. But we do use quite a lot. So maybe there's an even more efficient solution out there. But it's this balance, it's this trade-off between memory and time. Because, for example, this visited set is unnecessary. The algorithm will still work without this visited set because we can just change that to visited list, delete that, and this algorithm will still work. But it would be much slower. So we've added a bit more memory by creating this set, and in turn, we've made the program much, much faster. So it's this trade-off between memory and speed, and you need to balance both such that you achieve both of these constraints. So always keep that in mind, and always keep in mind sets, dictionaries, loops, and that type of thing, because that's how you figure out how long your program's going to take to run. Yeah, that was a really tough problem. We're now at the end of this year's series, and yeah, just have a play around with it, do cool questions, and really make sure you have an intuitive understanding of how this works. So the next time you see a similar problem, you'll be at it much faster.